So the next style of programming we cover is imperative or mutable state. And it's maybe the most interesting application of what we're seeing in this lecture. Because very often when we do, when we program in the pure functional style, we end up in situations where we really wish we could modify the value of variables. And then monads help us simulate that. So I'm going to show a concrete example or a semi-concrete example to make my point. So I need to go to the Hitchhiker's Guide, sorry. Let's see, new share. There we go. Right, so here we have the mutable state. So actually this is, it says 1.6, but I'm in chapter 6, so this is going to be 6.6 for you. I was just compiling the chapter alone. So here you have a function that's quite typical in functional programming. Let me zoom onto it a little bit. Which takes a context and argument, which contains all sorts of things, you know, like it's basically a repository of all your global variables. And it returns a context, but this is the old context, this is the new context, and this is the return value of the function. And this is, you know, additional arguments would go here. And then, so this is welcome new user, and it calls 3 other functions that are written in following the same idiom, which is again very common. So for example, the Isabelle proof assistant, its entire source code is written in that style, you know, in pure standard ML. And then what happens is you start with this context here, you give it to the first function, you get the context prime back. Context prime becomes context prime prime, prime prime becomes prime prime prime, and at the end you return prime 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 yourself. So you're threading the context through is what we call it, or in German durchnudeln. So then context durchnudeln. It's very hard to pronounce. And you see you have lots of bureaucracy here. This is just quite ugly, and you have to be careful with counting the primes correctly. If you forget a prime, for example, here, then the changes made by this function to the context will just be lost, right? And this happens all the time. So what we can do instead, using the monadic style, is to write a program where this bureaucracy with the context is hidden. So this is a new version. This is its type. If you look at your own version of the Hitchhiker's Guide, then the context here will be shown as a parameter here, and that's wrong. So that's a typo. So I fixed it here for this lecture, and you know, maybe we'll fix in the it will be fixed in the next version of the Hitchhiker's Guide for sure. But you see here, we can just completely forget about the context, right? We just declare it here, we declare it there. But then afterwards, we don't have to specify it here, we don't have to specify it there, we don't have to thread it through, we don't have to return it at the end. It's all implicit. You've managed to get rid of all the bureaucracy. And so this is what you achieve with a so-called state monad. Okay, so I'll explain the rest in lean. There. So what's a state monad? Well, it's based on the concept of an action. So an action takes, you know, has this signature: old context or old state, and then function arrow, return value, new state. And you remember the 4 functions we saw, so the one we defined and the 3 that we called, they all follow this pattern of ending with an action and then having some additional arguments potentially before the action, but they all ended with this exact pattern, right? So this captures it, right? So if I go back to my example here, let's see, again, I should not move so often between the windows, it's tedious. So instead of all of this, I could have said, well, what I have really is an action, you know, where the state is context. No, instead of all of this, I could have said it's an action with state is a context and the this. and the value is that part. So that would have been more concise, but I would have had to introduce action first, right? And it takes the state first, right? So that would be action of context and of that thing. So that's action. This is a type synonym really. It's a definition, but it's just saying, this type equals that type. And Lean is going to treat the two as the same because they're the same up to delta conversion. So definition expansion. So it's not a big deal. And then we define some custom operations, read and write. So read will simply take the state that we get, and it will return it, and it will leave it alone as a state. So we don't modify the state, and we return it to the caller. As for write, well, write takes a new state S. It ignores the old state, and as new state it puts S, and as return value it puts the single possible value of type unit. Basically, this is a void function, if you like. Okay. And then we can implement also the monadic operations pure and bind. So pure takes a state, and well, it takes a value first, then a state, and then it bundles them together so that they have the right type. So pure doesn't modify the state, right? That's the essence of pure. It should just put A in a box and leave the state alone. And here you have bind. So bind looks a bit intimidating. So we have a program MA and a function F, right? And we bind the two, we combine them. So we first run M of A, but M of A needs a state to run. So we give it the state that we've received, and then it produces a state S prime. And then we pass that state S prime to the next function. And indeed, this is exactly what we were doing manually in our welcome new user example, right? We're manually, putting this, putting this on left-hand side of the kind of assignments, and then passing, the right states at the right place. You pass an S here, you update an S prime. Next time you pass S prime, you have to be careful. If you pass S, then you forget what you've done here to the state, and so on. So this is where that code is. This is the actual bureaucracy, right? It just looks a bit confusing because it's very abstract at this point, whereas the concrete example or semi-concrete example was nicer in this respect. Okay, then we register the whole thing as a lawful monad. This is a bit boring as usual, but there are some new challenges. Because actions are functions, we end up having to compare, we have equalities over functions, right? So if I do again a simp of this there, have f of a is actually a function because it also, you see, f takes an alpha and is then an action, but you remember that action is itself a function. So let's unfold action as well. Also in the premises, I see that I'm not very good at this because it did nothing. That's a bit of a disappointment. Okay, too bad. Right, so, but just thinking about it, action is a function, so we're going to apply funX so that we compare values. Usually that brings us forward. Then we intro that. And then the advantage is, you see, you have the bind with 3 arguments, and bind was defined with 1, 2, and 3 arguments. So to be able to unfold the definition of bind, we need 3 arguments, and now we have all 3 because we applied funX. And at this point, it's very easy. You could do it with simp, we could do it with REFL, right? Simp, I think we'll just, no, simp of, of bind, right? Oh no, this is not good. This is revealing some internals here. This match one thing is really not good. But it doesn't matter, even Refel can do it, so let's not think too much about this. Okay. Again, when one method doesn't work, you try another one. You don't, right? It's, I mean, obviously this was not the way to go. So I could investigate this, but I can also be okay. I'm too lazy, and I'll just right. Or you could say, well, let's try to unfold this part here. Maybe this action bind, this internal thing, bind match. I mean, this looks very iffy. No, we didn't make any progress. Okay. Oh, actually, here we do end up with pure in such a situation. And actually, what this, I guess we have to bite the bullet and accept that we have this kind of internal construct that shows up there. I'd forgotten about this. So what is this match one? Well, it's basically the definition of action.bind has a match here. And for some reason, Lean has decided to give it a name. So instead of just showing the entire term, it hides it behind the name. And I guess that's useful when you have huge terms and you want to, don't want to clutter the output with them. But here it's a bit annoying because we have to think, okay, what is actually this match? But because it's a match, the trick is, well, let's do a case distinction on the argument of the match, and then we'll see which branch of the match kicks in. In this case, there was just one branch, and then actually refo works. I think it doesn't work without, yeah. But anyway, this is part of the lecture. This is not homework, so you're okay. And then, well, I'm not going to look at this case. So I already decided that I hate the state monad from now on because it's trying to disrupt my lectures. And at the end, we have a small example, which is kind of neat because it shows some programming, but actual programming, not like semi-concrete programming with the welcome user and so on. This is an actual mathematical function. And, Herbert Boss is not going to object to this one. So what this diff list does, and yeah, I don't know why it's called diff list, but that's the name I've inherited through the years. It takes a list of integers, and then it returns a sequence of those integers that go kind of monotonically increasing, right? So 1 is okay, 2 is greater than 1, 3 is greater than 2, and then it's like, no, 2, you're out. So at the end, you're left with a nice monotonic sequence, and everything else has been weeded out, right? And you need a start value, which is like a kind of, okay, this is the highest value we've seen so far. And we start with 0, which is quite natural. So here you see the result of this evaluation is 1, 2, 3. And then at the end of that, it remembers 3 is the max value we've seen so far. So if you give it a 2 or if you give it a 1, it's not going to take it. That's what the program does. Okay, so its signature is, well, it takes a list as input. We've seen that, the list of natural numbers. And the action is, well, the state is going to be a natural number. The state is this number here. It's what we remember. Okay, this is the biggest number we've seen so far. It's kind of a variable you'd have in imperative program. And this is the result type list, right? So if the input is a list, then you return a list as well. And because you're in a monad, this action monad, well, you have to use pure. If it's a cons, then you read the state, right? Which is this value, which is 0 initially, this variable we have. That's the previous highest value. And if n, the head of the cons, is less than prev, then we want to skip that value and we continue recursively with the rest of the list, ns. Right, which is a famous train company, I'm told. Else, you here have to enter kind of monadic block what to do, because you have several statements in a row in the, it's a compound statement in the else. And the first thing you want to do is, well, update the max value. Then you continue recursively, and then you return, well, this time you want to include it, and you return the recursive result, right? So previously we just called the function recursively because we wanted to skip n. Here we have to call it and put the result in a variable and pass that variable, to a const, because we also want to include the n. And the order is very important. If you do this instead, then all of a sudden you see you get a different result. You have to update the variable before you do the recursive call, because the recursive call is influenced by that variable. Okay.